All right, welcome back everybody. In this video we are going to talk about information from section 6 of unit 4 of AP Calculus. We're going to talk about approximating values of a function by using local linearity and linearization. So we start here by talking about what local linearity is. Functions that are differentiable possess a characteristic known as local linearity, which means if we zoom in sufficiently on a point on the curve, even for a function that's nonlinear, it's going to start to resemble a line. So let's take a look at what that means here. If I go ahead and graph a function that I know is differentiable, let's do y equals x cubed minus 5x squared plus 7x minus 11 minus 4. There we go. And we see our curve here on our screen, and it's a cubic function. We know that this function is differentiable. The derivative exists everywhere, and hence it has the property of local linearity, which means that I can take any section of this graph, and if I zoom in on that section close enough, the graph starts to resemble a line. Suppose I want to start zooming in on the point 1, -1. And so let me zoom in on that region. 1, -1. Still looks very much like a curve, but as we get closer and closer with that, it becomes less and less of a curve and starts to look more and more like a line. So you see, even though I was at possibly the worst case scenario on that curve when I started looking at it, now it really does look like a line as I look at the point -1, 1. Okay, so any function that's differentiable I can do that with. Now let's suppose that I have a function that is not differentiable, like y equals the absolute value of x is not differentiable at this point right here, 0, 0. Since this function's not differentiable, that means no matter how close I zoom in on this point, it doesn't start to resemble a line at that point. So at points where a function is non-differentiable, local linearity does not exist. No matter how much I zoom in, I'm really getting in there, really small units here. But that's what local linearity is all about. Okay? Because differentiable functions have this property, it makes sense for us to use a line to approximate the value of a differentiable function close to a given value. Because since the function is close to a line, when I zoom in close enough, if we use a linearization, this line to make approximations, it is going to be very close to the value of the function when we're close to the point on which the linearization is based. Okay, what is a linearization? A linearization is a line that's found at a point that is used to approximate the values of a function close to the point at which the line was found. The point at which the linearization was found is called the center of the approximation. Okay? Now, am I still on screen? Okay, so in the box here you see the standard, textbook notation for a linearization. If f is differentiable at x equals a, then the approximating function L of x equals f of a plus f prime of a times the quantity x minus a is the linearization of f at a. If you really think about this, the linearization, all it is it is the tangent line to the curve at the center A, rearranged into a different form. You know, that tangent line is going to be y minus the y coordinate is equal to the slope times x minus the x coordinate. Well, now the x coordinate here is A, and the y coordinate is f of A, and the slope is the value of the derivative at A. And then if we just add f of A to both sides, it turns into this linearization form. And then we just changed it to L of x to signify that it was a linearization. So really, when we're finding linearizations, all we're doing is we're finding the tangent line at a particular point. Don't make it more complicated than that. The linearization is just the tangent line at a point. Why are linearizations useful? If we have a very complicated function that we need to find close enough values over and over again that are close to a particular starting value, we can use the linearization, which will allow us to calculate the values to a reasonable precision without nearly as much work. Okay, what limitations? Ooh, I found a typo. There's an extra I in there. What limitations do linearizations have? The biggest limitation to a linearization is the further we get away from the center, the worse the accuracy of the linear approximation is. Okay, so that's a whole lot of introduction to what linearizations are. Let's go ahead and we'll do a couple of examples related to linearizations. Example 1. Find a linearization of y equals 2 sine of x plus x squared minus 5x at x equals 0. Then use the linearization to approximate the value of the function at x equals 0.3. So I need to find a tangent line. In order to find a tangent line, I need two things. I need a point and I need the slope. The point is what I get when I substitute x equals 0 into the original equation. And when I do that, we end up with just the y coordinate being 0. Then I need the slope, which I get by taking the derivative of our function. It's 2 cosine of x plus 2x minus 5. And now I'm going to find y prime at x equals 0. That's 2 cosine of 0 plus 2 times 0 minus 5. The cosine of 0 is 1. And so we end up with y prime of 0 equals negative 3. And so our linearization is going to be y minus the y coordinate is equal to the slope times x minus the x coordinate, and we can simplify that into our linearization being the function negative 3x. Okay, so that's going to be the line that we use to approximate the value of the function. If we want to approximate the value of the function at x equals 0.3, we're just going to go ahead and substitute 0.3 into this function. And our linearization approximates the value at negative 0.9. Let's see how good that is. The actual retail value of this function is, let's see, 2 sine of 0.3 plus 0.3 squared minus 5 times 0.3. And the actual value is negative 0.819. So that's not too bad, especially because 0.3 is a little far away from 0 compared to, you know, how we will typically use linearizations. It's close, but not super close. All right, let's look at example 2, and then we'll call it quits for this video. Choose a linearization for f of x equals the square root of x in order to approximate the value of f of x at x equals 4.1. Choose a center of the linearization that makes it easy to evaluate both the function and its derivative. Okay, so we want to use the linearization in this example to approximate the value of the function at x equals 4.1. That means we want to set up a linearization at a value that's close to 4.1 for which the value of the function and the value of its derivative are easily calculable. Calculatable. I don't know. For which I can easily calculate those values. And the value that I would pick that's close to 4.1 that comes out nicely in the original function and in the derivative is I'm going to center this at x equals 4. It's very close to 4.1, and the function and the derivative are both easy to find when x is 4. Okay, so we centered our linearization at 4. We're going to go ahead and write it now. Y minus the y coordinate is equal to the slope times x minus the x coordinate. And so my linearization is going to be equal to, I add 2 to both sides, 2 plus 1/4 times the quantity x minus 4. And so now I'm going to approximate the value of the function at 4.1 using this. 4.1 minus 4 is just 0.1. A quarter of that is 0.025. And so the linearization approximation is that this value is going to be approximately 2.025. So that's an approximate for the square root of 4.1. If we type that in, oops, I need my decimal point in there. You see how close we are, and in fact, our approximation from the linearization was 2.025. The actual value, if I round it to 3 decimal places, is 2.025. And this is actually, I use techniques similar to this when I'm trying to estimate square roots. So it's a very effective technique creating a linear projection between two numbers in order to approximate square roots. So that's a pretty cool application of linearization here from a calculation standpoint. All right, that brings us to the end of this video. We're going to come back for a second video on approximating values of a function using local linearity and linearization. Hopefully I'll see you then when we talk about that one. Have a great rest of your day and enjoy yourself. Bye-bye.